touched and heard of that I won't be here tomorrow. I'll actually be here in the morning.
Like before you came in, I was like, I would have never missed a school.
He said, when's the last time you think you missed it?
Yeah.
Dude, I'm telling you,
I don't know what a joke is.
let me explain my theory one of these days.
About your superpowers?
Yes, it's weird.
Okay. Anyway, so if you happen to be Catholic, my uncle was Bishop Eugene Gerber, who's bishop of the diocese for a long time. And he passed away, and his funeral is tomorrow, and I've got to be one of the readings of the Mass, so I've got to be gone. So if you have any questions like over the stuff, I will be here at 6:30 in the morning, and I'm actually going to record. I'm going to record my first block class. Don't feel, slighted, okay? But I'm going to record my first block class with a review, and then you guys will just watch that review, and then you'll have like a packet of stuff to work on, set of review problems for the test on Wednesday. So you'll just watch the lecture that I'm going to give first block. They're not near as fun. I'm just going to tell you that right now. They're half asleep, so but bear with me. Maybe I'll try and liven them up. Oh, come on.
I'm half asleep.
Work. Anyway. So with that said, any questions on the assignment? Okay, so let's just talk big picture. Because 9 and 10 are all kind of fit together. So,
I stole
I actually threw some of the stuff away.
Is it right here?
Yeah.
Hey.
Okay. On any inclined plane problem, what are the 3 forces that are always there?
Parallel?
Okay, force parallel always acts which way?
Parallel to slope.
And
Surface.
Down.
down.
Okay.
Force parallel will never, ever, ever act up the inclined plane. Because this is just all force parallel is a part of the gravity that's acting down the inclined plane. Okay? So your gravitational vector always points straight down. Okay? Your force parallel is parallel with that surface, and then your force normal is going to be at a right angle to the surface. So these are the 3 that will always be there. Always be there. Now, you get any inclined plane problem. What I would suggest is that you set up a big chart. And you can actually use this for any force problem. Where you can have your force parallel, your applied force, your opposing force, and your net force. Okay? Literally, this chart is broad enough, you can use this with any problem. It could be a rocket, could be a horizontal problem, whatever. Because if you're shooting a rocket straight up, what force parallel is there? There isn't. You only have a force parallel if you're on an inclined plane. But with a rocket, you always have an applied force. When a rocket, what's your opposing force? Gravity. Well, if you're on an inclined plane, what's the only thing that will be your opposing force?
Friction.
Friction, right? Okay, that's it. So, here's what you want to look at. So, if you look on number 9, what are the 2 most important words in all of number 9? Constant velocity. Literally, here's what every force problem can only play out one of 2 ways, and one of 2 ways only. Either you're at constant velocity and all the forces add up to, and your net force is 0, or you accelerate. And then within the acceleration, you only have one of 2 things that can happen. Either the acceleration makes you speed up, and it's the same sign as your velocity, or it makes you slow down, and it's in the opposite sign. That's it. There is nothing else. Every force problem plays out one of 2 ways. Either you accelerate, or you're constant velocity. That's it. So as soon as you see constant velocity, you're going to make everything add up to equal to 0. So at number 9, your frictionless inclined plane. Oh, okay, right? Don't have to worry about this, okay? No friction. So that only leaves force parallel and force applied. So what's the only way these 2 forces can add up to equal to 0? Yeah, they have to be equal and opposite values. So as soon as you find your force parallel, then you know your force applied. Now, talk about number 10. What makes 10 complicated?
It's
Friction. But here's the deal. So on number 10, you're going to pull this thing up the inclined plane. So here's the first thing that I would recommend. Make this sketch. Okay? Make this sketch. And then decide within your system how you want to play the game. So obviously, you're going to pull this thing up the inclined plane, right? So your force applied probably is going to be acting up the inclined plane. So if that force applied, if you're going to define this direction as being positive, and I don't care how you set up your system, I literally do not care. Okay, I do not care. But if you're going to make your applied force a positive number, okay, then what's going to be the sign of your force parallel? Negative. That force parallel always going to be pointing down the inclined plane. Now, here's the kicker: is what you do with your force friction. No. What?
Are you busy?
Yes.
When are you not going to be busy?
Probably in about 30 minutes.
I'll come back.
Okay. So, okay.
intimidating, I guess.
So, which direction is friction going to act? Ethan.
It's frictional, it's going to go against parallel. So, well, no. It'll go down
Why?
because you're applying the force.
Not so much that. Which direction is the box moving?
Up.
Up. Okay? So it is, you'll see it isn't necessarily against your force applied, it's in the opposite direction of motion. So if you're pulling this thing up the hill, guess what? Your force friction is going to be going down the hill, and if you define that as being negative, that's going to be a negative number. Okay? So if nothing else, start with this, get your signs right, then worry about the numbers. Okay? Start with that thought process. So if all goes well, that answer to number 10 should be something around your first teenage birthday.
Wait, what?
Your answer to number 10 should be something around your first teenage birthday.
Yeah.
You just skip.
19.
Yeah.
24.
Okay. Make sure on those diagrams, do not draw your force normal pointing straight up. Your normal force does not point straight up. Your normal force points at a right angle to the inclined plane. Okay? That does not point straight up. Okay? Gravity pulls straight down. Your normal force acts at a 90-degree angle. Okay, got that, Hunter?
Can I get that sign, please?
What are the odds of coming back in to interview Hunter?
Huh?
What are the odds of coming to interview Hunter?
I won't go.
I'll stay.
Okay, once, twice sold, get those handed in.
Nothing.
I
He's looking at me weirdly.
I don't know why. Okay, so here's the drill. We got 2 labs today. And then we'll review tomorrow, and then the test is going to be on Wednesday. So on Wednesday, if you want a little bit of a head start on the test, if you want to come in like before the end of lunch, you can. Okay, so if you want to be a little bit, if you're a slow test taker, you want to come in early, you can. Okay, because I won't be here to remind you tomorrow, so just, Mary, this is your job to remind the class tomorrow. Because I have faith in you, okay? All right.
Don't do that.
You really think I'm going
Don't
to
do
trust
that.
Mad Max? No.
Yeah, she's no better to trust than I am. She's just as forgetful.
You can trust me.
Yes.
Okay, somebody remind somebody to remind somebody tomorrow.
Hey, don't forget
Why
to
don't
tell
you
somebody.
just Why don't you just write it on the board?
I'll
I'll
remember.
forget to write it.
I'll remember exactly
What do you think? You think he's gonna think ahead or something? What
Okay,
are you
No,
nuts?
who would do that? Who thinks who would do that?
so kind of a quick refresher.
A nerd.
So if I lift this up, okay, and set this up like this,
My apologies.
Yeah, you're bad.
Very much.
why doesn't the block slide?
Friction.
So does every applied force cause an acceleration?
No.
No, look at this, right? I've got this force parallel pulling down the inclined plane, but it's not accelerating. Because what? Or at least the same, right? Okay, it's enough to hold it in place. So if I lift it higher, what's going to happen to my force parallel?
It's going to get greater.
It's going to increase. Now, at some point, if I lift this up, what's going to happen?
It's going to start moving.
It's going to start to slide. Okay? Bye-bye. Now, so here's what we're going to assume. So by the way, a quick refresher. What do you call it when the type of friction when you're moving from rest?
Static.
Static. So here's what we're going to assume. Is that split second where it just begins to slide, that force parallel acting down is just balancing out the force friction acting up. Okay, so that's the assumption that we're going to make. At that very instant, those two forces are equal. Okay? So here's what we're going to do. We're going to look at this and go, okay, mu is the ratio of what? Force friction over? This is not force net. Some of you are confusing this normal force with force net. Your normal force will never be your net force. Ever. Okay? Ever. Your normal force is never your net force. Ever. In any situation.
What about in deep space?
You have to have a surface to provide the normal force, and that's balancing out a gravitational pull. So, it's just, no. Okay, so here's what we're going to do. At that point that it just begins to slide, we're going to set that force friction equal to this force parallel. So how do you calculate force parallel?
The sine.
FG
Theta.
sine theta. Now, on some of yours, on that derived equation, on that lab that I just gave back with the table being pulled, some of you are taking m1 times fg. You cannot multiply a force by, or mass by a force. You can multiply mass times gravitational acceleration, but you cannot multiply mass times a force. It doesn't make any sense. Now, how do you do force normal? Fg cosine theta. So, what's going to happen to your forces here? Now, for those of you that have done trig identities, what's sine over cosine? Tangent. This is the only time you use trig identities outside of the classroom. This one instance right here. You will never ever use it again.
Ladders for like
They got to justify their jobs. Okay. So, physics you use every day. I mean, literally, of all the sciences, physics is the one you use every day. Oh, I've got to drive. I've got to accelerate. I've got to stop.
Is that why you taught it? Yeah, biology?
That in school. Biology, whatever.
I've got to breathe. My heart has to beat.
I said it's the only real science you use every day. So, I'm just saying.
I want to get him and his husband to argue about this.
Oh, we have. Believe me, we have. Okay.
I know. But it'd be fun to watch.
He's wrong,
Okay.
but he would.
So mu equals tangent theta, right? So here's the deal. So if you're, this is what you're going to do in the lab. So you're going to lift this thing up until the block just begins to slide. Call me over. I'm going to take my phone. We'll measure the angle. So let's say that that's 15 degrees. So somebody take the tangent of 15 degrees.
0.268.
So 0.27. So that's a coefficient of static friction. It's the easiest one to do. But listen to me, that only works with static friction. Okay? Now, once you get done with that part of the lab, you are done with the lab and you will never speak of that again. Okay? It's done. So, Let me hand out the lab and I'll show you why it doesn't work. So stop that. So
I'm
that's going to
hungry.
be the first part of the lab. You're going to lift it up until it just begins to slide. Call me over or use your phone, whatever. Get the angle. That's all you have to do. Take the tangent of it, you're done. The second part is going to be more complicated. So the second part, you're going to take the cord and you're going to set it at exactly 30 degrees. So this is going to be a known angle of 30 degrees. I'd take like a ring stand and a rod to kind of hold that up so you can brace it at exactly 30 degrees angle, 30 degree angles. Don't try and hold it. So after you get it set at 30 degrees, which is going to be about like yay, then you're going to take a block and let's figure out what you can, what information can we gather about the block?
It's mass.
It's wood. Okay?
It's weight.
It's weight. How can we get the weight of the block?
Newton scale.
It's a Newton scale, right? We happen to have one handy. Being a physics teacher, I never leave home without one. Okay, so this thing has a weight of 4.00 newtons. Okay? So, we got the weight. So if I know the weight, what else can I determine once I know the weight? I can find the mass, right? If I know the angle, then when it sits here, I can also determine
Force normal.
force normal and
Force parallel.
force parallel. Which direction is force parallel going to act? Down. Okay. So you're going to set this thing at exactly 30 degrees. You're going to take a Newton scale, which you're going to re-zero. You're going to pull it in this direction. And you're going to set it at 30. And you're going to pull it up at a constant velocity, which is about 2.4 newtons. So what am I measuring when I'm pulling this thing up at a constant velocity? Am I measuring FAP, force parallel, or my force friction?
Fat.
FAP. That's your applied force. So one of the things that you have to decide, and that's, if you look on that green sheet, one of the first things that you have to do up there at the top is to decide how you want your system to play out. Okay? Do you want up to be positive or do you want down to be positive? I don't care. But once you stick with it, once you assign that system, you have to stick with it. Okay? So if you're going to go with the torus system, you're going to define down as being negative and that applied force is going to be positive. There are no right or wrong answers. Just pick one. Okay? I don't care. But once you pick one, you have to stick with it. Okay? All right. So when you look at this block, I had some applied force going up, which was about 3.20 newtons. So, what forces are acting down the inclined plane?
Force parallel.
Force parallel and
Force gravity.
force friction. Well, gravity is going to be acting straight down. Okay? So you're going to have force parallel, you're going to have force friction, and there's another force that we need. Normal force, right? So one of the things you're going to do is you're going to draw a vector diagram, and when you get done, it's going to look something like this. You're going to have a total of 5 forces. Gravity, parallel, friction, normal, and your applied force. Okay? That's what you're going to have. So when you get done with it, and I tell you, draw this at exactly a 30-degree angle. So when you make this, you draw this at a 30-degree angle. You set up a scale going, hey, I'm going to let 1 centimeter equal a newton, whatever it is. And then you're going to draw that vector diagram. You can either draw it on the back, or you can do it on another sheet of paper. So let's talk about this 3.20 newtons. So one way to generate that force is to take a Newton scale, grab it, and pull it up. The other thing that I can do, and this goes back to the horizontal lab that I just gave back, I could suspend a weight from the end and let that gravitational pull drag this thing up. That's another option, okay? That's another option. If that's the case, how much mass would I have to put out here to generate 3.2 newtons of force? How can I figure out how much force, how much mass that would take?
Divide that number by 9.8 meters per second squared
Beautiful. Why?
to get the mass that would make it have constant velocity.
Beautiful. Because let's say, well, it's like, oh, I like 1 kilogram masses. Good, I'm happy for you. Okay? But if I take a 1 kilogram mass and suspend it from the end, how much force is that going to apply?
9.8.
9.8 newtons, right? It would accelerate. Okay, I'll concede that maybe a half a kilogram. Well, that's cute. I'll put 0.5 kilograms. Well, if I put 0.5 kilograms, guess what? That's going to be
4.9.
still going to be too big because that's going to be 4.9. So, and there's going to be a problem like this on this letter. So if you want to figure out what mass you take to generate a certain amount of force, take the force that you need, divide that by 9.8 meters per second squared, boom, there's your mass. Okay? Got that? Yeah. So, getting the data for this, listen to me, get the data quickly. Lift it up, measure the angle, boom, you're done. Hold it at a constant velocity of 30 degrees, get the weight, boom, you're done. Do all the calculations later. Now, let me hand out the second lab. So, knock that.
You know.
It's okay.
You're very like, ooh.
Labor cam.
Everyone else saw that a week ago, Vonda. Oh, is that a magnet? That looks like a magnet to me.
I'm sorry if I've ever offended you.
Okay. So here's,
Don't play with this
okay. So here's the first word of caution about these labs. This lab is involved, this particular part is going to involve a very, 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 very strong magnet that will wipe the memory from your magnetic card on your credit cards. There's a magnetic strip that will wipe it out. Okay? This magnet is rated at about 150 pounds, which means that if you weigh 150 pounds or less, I could attach this to you and lift you up. Okay?
That's so cool.
Can we try that?
Good thing I weigh less than
I'll move my wall.
Are we sure this thing works? Can we test it?
Just show up.
It's like a dollar on this.
Here.
That's
Okay?
a dollar that you won't have after this.
Okay.
Man.
So, shh. Okay. So, here's the cool thing about magnets. Well, there's any number of things that are cool about magnets. So, if I take this, and this is actually aluminum. So, aluminum is what's called a non-ferrous material, which means that the magnet itself isn't attached to it at all. But if you put it like on that, it's very much attached because that's a ferrous material. Okay. All right. Now, there's a couple of things that you want to keep this away from. First off, keep them away from other magnets in this room. Because if we stick two of these together, I have to take them down to the shop, put them in a vise, and pry them apart. Okay?
That's something.
Yes. So keep them away from any other magnet in this room. Now, but if I take this magnet, and it's not attracted to the plates at all, but if I take this magnet,
Magic.
Physics.
okay? So here's the deal, is that without going through an entire day-long lecture on electromagnetic theory,
Can we?
here's the short version. Basically, Mother Nature hates things that are out of balance. So if the magnet isn't moving, it doesn't have any effect. But as soon as I move it, what happens is that it creates this aluminum foil senses a change in the magnetic field because this thing is moving. That induces, very briefly, an electric current in the aluminum plate that opposes this magnetic field. That's why it's a braking effect. So this is what's known as ferrofluid. And so if I bring this close, okay, it does a nice job of showing that a magnetic field is composed of lines. And so when I bring it closer, you'll see that the field lines are very, very dense. But if I move them farther apart,
That's so satisfying. You should.
Yeah.
Yeah, we should make another YouTube channel.
Instead of slime.
just the ferromagnetic fluids.
Yes.
Okay, here, John, hold that.
Okay.
No. So then, no, I got to blow off. No, move, sweetheart, hold it light. There you go. So if this one's a lot weaker, but then if I put it over here, hold on. then if you look in the middle, then it becomes like a solid.
That's so satisfying. Keep going. It's satisfying.
All right, so put that back up. Okay, now, so here's what you're going to do in the lab, in terms of the lab itself. First off, you're going to do some simple experiments with this. So even if I take this and just let it swing, okay, swings pretty freely, not a big deal. But if I take that same thing and then let it swing within these plates, it just acts as a huge brake. Now, I'm trying to do this. Hold on. Let me move this back.
Oh, you got it one of these times.
I'll get it. There it goes. Okay. So what happens is that, again, it creates this braking effect. So that's one of the things you do, simple deal. Let it swing and then see what happens afterwards. In terms of the data collection, what we're going to do is we're going to try and get an idea of how much force is generated by this magnet. So the first thing you're going to do is the magnet is not going to be involved at all. Okay? So what you're going to do is you're going to have this block, and it's going to say top on it. Guess what?
That's the top.
That's the top. Okay? That's the top. I know, radical concept. So you're going to put this, I don't care which end, you can put it out here, we'll put it on this end. Okay? So once you get that set up, give me a call, I'll take my phone, we'll get a reading. So then what you want to do is set this up where, and I don't care what distances that you need, it just needs to travel 40 centimeters. So if you're clever, what are you going to let the initial velocity be? Zero. So you're going to start here like this, right? And you're at 50. You're going to let go of it, and you're going to let it go until the front edge hits the 10 centimeter mark. Because that 40 centimeters is the length of these aluminum plates. So you're going to do that 5 times. Boom, line it up. Boom, stop it. Do that 5 times without the magnet involved at all. Then you're going to set the magnet in here. And let me give you a hint. This thing is very much attracted to this metal rod. And if you're not careful, it'll get stuck against it and it will make this loud noise and everybody's going to go, okay? So, it's going to happen. So when you do this, what you're going to do is you're going to set this up where this thing can roll through unimpeded without hitting the sides of the plate, because then you don't know what's generating the force. You don't know if it's coming from the magnet rubbing against it or just the effects with the aluminum plates. So you're going to set this up, and then you're going to run this again with this thing going through the plates. So you're going to have 2 distinct sets of times. One without that magnet, and then you're going to run it again with that magnet in there. And then you're going to make a comparison. So that's the data that you need. Couple groups start with this, get your data, and then switch over to the friction part. Some other groups start with the inclined plane part, and then switch over to this one. So with this one, when you get done, when you get to number 8, this is the only time I'm ever going to tell you to do this. When you get to number 8, you're going to draw a vector diagram that shows all of the forces acting on the system. But with this one, you're going to have 2 really jacked up and completely different scales. So your scale going vertically and normal are going to be really big numbers, probably around 10 newtons. So on that one, I'd maybe let 1 centimeter equal a newton, maybe even 2 centimeters equal a newton, something like that. Or excuse me, 2 newtons equal a centimeter, something like that. But your forces along this, because it's such a shallow angle, are going to be really small. So I'd choose a different scale for that one, because then you want to be able to draw like bigger vectors and make them bigger than what they actually are. So maybe let 2 centimeters equal Newton, 3 centimeters equal Newton, something like that. So show me each distinct scale. Have one set, say, okay, here's how I'm going to lay it out along the inclined plane, here's the other one that I'm gonna use for force normal and my gravitational force. So this is the only time I will tell you to set up two different scales, but it's only because the numbers are so vastly different. Okay, I'm done, you're on your own, be free.